All right, hello guys. Today we are doing video number 6, graphing logs. Okay, so let's just get into it. Let's see, here we go. Yay! Okay, so we're going to start by looking at our exponential function y equals 2 to the x. And we're just going to fill out our function table. We've already done this before, so we should be pretty quick with it. All right, so just plugging in -2 to the function y equals 2 to the x, we get 1/4. This is going to give us 1/2. This gives us 1, 2, and 4. All right. I'm going to pause and let the thingy catch up. Okay, so now all of our values are up there. All right, what we're going to do is we're going to go ahead and we're going to graph this function on our provided grid. All right, so we end up with, all right, and we already did this in the exponential functions video, so if you need a refresher, you can always go back and take a look at it. So here's our asymptote, and we've got this point, this point, this point, here, and here. All right, so here's our exponential function, y equals 2 to the x. All right, y equals 2 to the power of x. All right, now for the inverse, we're going to look at, we're going to use some of the properties that we talked about with inverses in our last video, which is our coordinates are just going to have a swapped x and y value. So we can go ahead and we can do our inverse coordinate points. All right, so -2 1/4 becomes 1/4 -2. All right, 1/2 -1, 1 0, 2 1, and 4 2. So those are going to be our new coordinates for our graph. We can also go ahead and make our inverse equation by swapping our x and y's and then solving for y. So for this one, our base is 2, so it would be log base 2 of both sides. The log base 2 of 2 cancels, and so it leaves us with y equaling log base 2 of x. So this is our equation now. So there's our inverse equation for our original exponential function. And then we also can graphically do our inverse by sketching in that line y equals x, all right, which would be this line right here. So this is that y equals x line. Right, and we're just going to use that to reflect everything over. All right, I'm going to plot these new points. Let's use bright green. That feels right. All right, so we're going to plot. So 1/4 -2. So 1/4 -2 somewhere around here. 1/2 -1. 1 0. And then we have 2 1. And we have 1 2 3 4 1 2. All right, now our asymptote that we did have at y equals 0, we are also swapping that one, right? So if it's y equals 0, originally the inverse would be x equals 0. So we get this vertical asymptote right here at x equals 0, and then our graph is going to follow our asymptote and curve straight up. And you can see, I know my head is a little bit in the way here. Hold on, let's just move it to the side. There you go. All right, and now you can see that we definitely do have like a reflection over that line y equals x. Our coordinate points have just been swapped. All right, and so now we have our inverse equation. This is the graph of our log function. All right, so let's go ahead and fill in some key features. All right, so first let's do it with our exponential function. So our exponential function is going to have a domain of all real numbers, okay, -infinity to +infinity. The range for our exponential function starts at 0 and goes to +infinity. All right, our x-intercept is none because we have an asymptote there. Our y-intercept is that point 0, 1, and the equation of our asymptote is y equals 0. All right, so that is our exponential function. Now again, if you are confused on any of those values, please go and see our video on the exponential function. All right, so now what we want to do is figure out our inverse information. All right, now remember, inverse means doing the opposite, right? We're swapping our x and y values. I'm just going to move my head up here. All right, so if our domain of our original function is negative infinity to infinity, and we're swapping our x and y values, that means that our range of our inverse would be the same as the domain of the original. So our inverse domain is negative infinity to infinity. All right, if the range of the original function is 0 to infinity and we're just swapping x and y's, that means the inverse should have a domain of 0 to infinity. And if we go to the graph, you can see that, right? So our x values start right there at 0. So, right, we're starting our x values right there at that asymptote, right? And then they're going to go forever in the positive direction. Our y values are going all the way down, right? There's an arrow pointing down, so we're getting all the negative y's. And even though it's growing slowly, it is going to eventually go all the way up, right, to positive infinity, right? So we have one end pointing to positive infinity. Eventually it's going up there, and the other end is pointing down, which means our y values are negative infinity to positive infinity. All right, so next up, all right, x-intercept versus y-intercept. So again, we're swapping x and y's. If our x-intercept originally, for our original function is none, that means that our inverse should have no y-intercept. All right, which makes sense because we have an asymptote on our y-axis. All right, so for our y-intercept, if we originally had 0, 1, the inverse is just swapping those x and y values, so it's going to be 1, 0. All right, and you can see if you go up to our equation, right, our table of values here, we do indeed have that coordinate point 1, 0. Awesome. All right, last but not least is the equation of our asymptote. So the original function had y equals 0. Our inverse is going to have x equals 0. All right, so that's our inverse relations kind of being applied here to our log function. All right, transformation rules. I'm going to go through this really quick because they are the same exact transformation rules that we had for our exponential functions and we've used before in previous units. So this time I'm just going to replace the function piece with the log part. So we've got x minus c over b plus d. And just remember this, we use a b here because this is our base number, b for base number. It's not a transformation, all right? I could put any number in there as a placeholder if I wanted to, but I don't want to confuse you and think that when you change that base number, it's a transformation, because it's not. All right, that little b right there at the subscript of my log stands for base of my log, not for like the b that's my horizontal, right? So really quick, this is our vertical dilation. All right, a negative a is a reflection over the x-axis. All right, b is our horizontal dilation. A negative b is a reflection over the y-axis. All right, c, this is my shift left or right. A minus c is moving to the right. A plus c moves you to the left. And then d is my shift up and down. So a plus d is moving up. Oops, forgot the plus part. All right, so plus d moves you up, minus d moves you down. All right, so the big things here are going to be what is shifting the parts of the graph that you guys really need to care about. All right, one part is our asymptote. All right, so for our asymptote, right, we have a vertical line. A shift up and down doesn't affect a vertical line. A stretch isn't going to affect our asymptote, a vertical line, right? A stretch sideways is not affecting a vertical line. So then the only transformation that's going to affect your vertical line is a shift left or right. So your asymptote is just going to be y equals your c value. All right, now, if you have a minus c in there, that means your c value was positive. If you have a plus c in the equation, it means your c was negative. So it's whatever your shift is, right? So if it's, just be careful, it's always kind of the opposite sign, all right? The last part is you're going to be transforming the x-intercept point, all right? So your x-intercept, all right, to find this point algebraically, all right, just like we had with the last one, we had like an algebraic trick. This one is the same kind of deal. So you can use transformation rules. I'm going to walk through how to do transformation rules as well, but you can also do this algebraically. What you're going to do to find your x value is you're going to take the inside of the log, and equal it to 1. All right, so that whole x minus c equals b part, you're just going to take whatever that is, you're going to equal it to 1, and you're going to solve for x. All right, then to get the y value, you just plug in that x value, right? So just plug in the x value. All right, spoiler alert. It's always just going to be whatever d is, all right? And that's because when you take the inside of your log and you equal it to 1, the value of a log base, whatever, of 1 is 0. So it would be a times 0 plus d. So it really just always ends up being d, right? But you'll learn that pattern as you go. All right, let's take a look at an example problem. All right, so here we go. So here's our first one. This one's kind of easy. All right, so we'll just walk through it. So we want to figure out the different information for this one, and then we want to go ahead and we want to graph our function. So first off, I know that I have 2 transformations. All right, one of the minus 2 is moving me to the right by 2. All right, and then the plus 1 is moving me up 1. All right, so right 2, up 1. All right, remember this 3 is not a transformation, okay? Not transformation. All right, so moving on to the next part, trying to find our asymptote. Remember, that's going to be whatever your c value is. For our problem, our c is 2. So our asymptote is x equals positive 2. We're moving everything to the right. What way is right for you guys? Right? Nope, that's left. That's right. Whatever, it doesn't matter. Moving to the right by 2. All right, so there we go. And I'm going to go ahead and just put that in my graph. So now I'm going to sketch that asymptote. So x equals 2. Awesome. Now, I am going to walk you guys through how to do the transformations with this one because I think they're really easy. All right, so once you move your asymptote, the point is always 1 away from your asymptote. So here's where the point normally would be. All right, so it's always 1 away. Now, if you have a horizontal stretch, that's going to affect it. A vertical stretch is not going to affect your new 1, 0 point. All right, because if your y value is 0, if you try and stretch 0, it doesn't do anything. 0 times anything is still 0. All right, so the only thing you're really looking for stretching for this one would be a horizontal stretch. All right, but it also does need to move up and down. All right, so it's already been shifted to the right by 2 because we shifted our asymptote. All right, but now we need to move that point up 1. So here, come back here. There we go. No, stop. There we go. All right, so that point has been shifted to the right by 2 and it's been moved up 1. So now we don't have any other transformations. We've done them both. We can just go ahead and sketch our log function. All right, so our new point is 1, 0. New 1, 0 point is now 1, 2, 3, 1. Now, doing this algebraically is also pretty easy. You're just going to take whatever's inside the log, which in this case is x minus 2, and you're going to equal it to 1. All right, you're going to add 2 on both sides, so you have x equals 3. All right, which, hey, ta-da, that's what we got when we did it with our transformation rules. All right, now to find the y value, you're just going to plug in that 3 into your equation. So it's log base 3 of 3 minus 2 plus 1. So that is log base 3 of 1 plus 1. Now, right here, log base 3 of 1, this is saying 3 to what power is 1? Well, 3 to the 0 power is 1. So you get 0 plus 1, which is just 1. And that's what we got. All right, and like I said, you can make that connection, right? This number is always going to be equal to that number right there. They're always going to be the same. All right, but yeah, okay. Last but not least, domain and range. All right, so for your domain, you need what's inside the log to be greater than 0, right? Because you can't have anything inside the log being 0 because there's no, because think about what that means, right? So you would say 3 to some power equals 0. Well, that's impossible. There's no number you can raise 3 to and get a value of 0. So whatever is inside your log must always be greater than 0. So that's what we're going to do. So for our domain, we're just going to say, okay, well, log, we don't need the log part. We just need what's inside of it, which is x minus 2. This has to be greater than 0. All right, and then we just solve. So x has to be greater than 2. Well, we already knew that. If you're looking at the graph, you can see your asymptote is at 2. Therefore, it can't cross the asymptote, so it has to be greater than 2. All right, so you could just do it by looking at your graph, but that's how you would do it algebraically. Some of them get a little bit confusing, so it's always good to know like how to algebraically calculate it. All right, so you just need the inside of your log to be greater than 0. All right, so for this one, we have 2 to infinity. Now, range, no matter what log function you're dealing with, your range is always negative infinity to positive infinity. The range never changes. Negative infinity to positive infinity. Okay, so that's example number 1. I'm going to show you one more example, and then that'll be it. All right, so this one has a little bit more, some more transformations. It's got a dilation in there, so I like to go over these ones. All right, so we'll just go through pretty quick. Actually, I want you guys to, what I really want is I want you guys to try this one and then pause the video, and then when you think you got it, unpause and take a look at what I've got. Okay, check your answers and see what you got. All right, so our transformations are left 3, horizontal dilation by 2, and down 4. Our asymptote is going to be at x equals -3. Our new point is -1, -4. All right, so I have the calculations for finding the x value to the right. All right, I just highlighted it for you guys, right? So it's right there. But you can also just, like I said, calculate this by doing the transformation rules. So transformation rules, remember you're starting 1 away from the asymptote. So you move your asymptote first. You would then be 1 away, which would put you right there where I just put that little dot. There it is. All right, so then what you want to do is you want to dilate away from the asymptote by 2. So 1, 2, so now the point would be in that second dot that I've got right there. And then we just need to shift it down 4. 1, 2, 3, 4. And that lands right where the point is. All right, so I shifted left 3 because I followed the asymptote. I then dilated 2 away from the asymptote. I then shifted it down 4. All right, so that's how you would do that one. And then I just sketched it. It's going to go towards the asymptote, and it's going to kind of continue growing as it goes to infinity. All right, well, I hope that was a good video and it was helpful. And now you should be able to do homework number 6. All right, bye.